Good afternoon, everyone. Thank you for joining us this afternoon. So I'm Bryce Powdrill. Joining me on stage is Kalina Krizak. Just really quickly on who we are, and I know those of you who attended Stuart's keynote would have seen this, so I'll just run over this really quickly, but we are Queensland government-owned transmission network service provider. We own, develop, operate and maintain the high voltage transmission network ranging from up to Cairns down to the New South Wales border. And serving over 5 million Queenslanders and almost 250,000 businesses. So when we talk about modelling Queensland future energy pathways, what we're really talking about was our work that we did to identify achievable future Queensland generation and transmission system development pathways to reliably meet future needs while minimising long-term costs on consumers, and determining from this what were the low-regret early actions. So when we think about the range of sensitivities that we want to test, they really fall within these 4 broad buckets: deliverability, government policies, forecast uncertainty, and power system requirements. And then underneath each of these, we've got a whole range of sensitivities where we want to seek to understand the impacts and trade-offs through additional scenarios. Approaching this without a plan can result in significant wasted time and resources. So in the next few slides, I'll give an overview of our modelling approach, as well as the rough amount of simulations we ran under each step to help us get a better understanding of the question that we were trying to answer. So we're very conscious that market modelling is highly assumptions-driven and hyper-optimal, which can give an unrealistic estimate of the time required for the investments. Therefore, we apply the layered modelling approach that levels on layers of detail to address some of these critical modelling limitations. So Stuart presented a kind of high-level view of this layered modelling approach, and this is the deeper analytical level that we apply in our modelling. So the left-hand side shows our layered modelling approach, and the chart on the right shows on the left-hand axis a broad approximation of the number of runs we did under each step, and on the right-hand axis, the relative amount of credits that we used. So under the academic linear optimization step, this really provides the starting point for the optimal least cost expansion where all the build decisions are linear and unconstrained to help narrow down what questions we're trying to answer, as well as test and develop the model framework. Here we're probably doing in the range of the high tens to hundreds of runs, using a relatively lower granularity, so maybe an 8 load block, with results primarily focused around understanding capacity build. When we move into the linear sensitivity analysis, here we're talking hundreds of runs into the many hundreds of runs and quite significant credit usage. This is probably where we spend the most time because we're really trying to explore the energy landscape and understand the drivers, explore what the model sensitivity to changes are in the key assumptions, what are the trade-offs in the build and generation outcomes, as well as how robust these outcomes are and what point do the solutions pivot. Under the discrete base case step, we know that some critical investment decisions like transmission build are not linear in reality. So based on the learnings from the previous steps, we start testing and locking in discrete timing and sequences of options. And here we might start to increase the granularity of our results, but reduce the total number of runs as we're starting to narrow down what the potential options for the future pathways might be. So again, in the high tens to perhaps low hundreds, and a reduction in credit usage. The deliverability constraints are overlaid to identify credible, achievable pathways. These sensitivities are overlaid on the discrete base case, and they help to overlay what are credible deliverability constraints, such as how much wind you can build per year, how much transmission is feasible to be delivered in each year. And then next, we move into the discrete sensitivities where we start to answer the what if, and more credibly answer the questions posed at the beginning. This is where we start to see credit use creep up again, as well as our run count, because not only are we increasing the number of runs, but we're starting to increase the granularity of the results that we're seeking to understand. And we're starting to pay much closer attention to the dispatch outcome trade-offs. Next, we apply what we call a lock and shock analysis, and I've heard people refer to this as different things, but effectively it's, the lock and shock, where we stress test the system to ensure it's resilient to what we call the known unknowns, like perfect foresight, as well as the unknown unknowns, like weather variability to real-world conditions. Here, when we start locking in results before rerunning our simulations at a much higher granularity, we see slightly lower credit usage, but for a similar amount of runs. And then finally, we call this realistic dispatch, but obviously all modelling is a forecast, so it's a representation of the highest granularity of our modelling results, which based on our learnings demonstrates a range of credible, achievable pathways to satisfy our questions of what are least regret early actions for affordable, reliable and a sustainable system. So this is our modelling approach, and then beyond this, we overlay our interface with our system planning software, PSSE, where we assess load flow power system analysis and power system security. And I'll just touch on this really quickly. So in all market modelling, we make simplifications to the model for tractability reasons, because we know at some point you reach diminishing returns between the time and cost to build the model versus the cost to run the model. And when we're assessing outcomes from this, how can we be confident that we haven't oversimplified the system and the results we're getting are plausible, not just from a system build perspective, but also from a practical operability perspective? So this is where we work closely with our system planning team to create this feedback loop which uses the Plexos market model results and feeds them into PSSE to check the outcomes we're getting from Plexos are realistic and achievable from an operability perspective. The outcomes from the PSSE studies are then fed back into the market model, usually in the form of constraints, and this feedback loop happens continuously throughout our process. This helps to identify not just the operability issues in our market modelling, but also helps our planning team to understand how realistic future pathway development options are from a least cost perspective and plan potential network upgrades accordingly. So what do we learn from all of this? So a balanced mix is required for the evolving energy system, and considering the speed limits to the development of new resources, our modelling identified several low-regret early actions that facilitate optionality in an affordable, reliable and sustainable system. These include, in no particular order, facilitating the early development of wind generation, increasing flexibility and shifting demand to daytime where possible, recognising that existing coal-fired generation will be required until sufficient replacement resources are operational, targeted transmission augmentations and works to better utilise the existing network, facilitating energy storage depth over capacity, that is gigawatt hours over gigawatts, and prioritising flexible gas power generation. If we dig a little bit deeper into some of the results that we presented, and this is just a really small subset of our results, and in the interest of time, I'll just focus on a couple of key takeaways. So the chart shows the range of capacity outcomes by year for the final set of modelling results that we ran when we were modelling future Queensland energy system pathways. And so the colours show the different technology types. But if we focus on the gas build by year, which is shown in orange, we found that the prioritisation of the early build of flexible gas generation was a least regret decision. The range of gas build under all scenarios was relatively narrow and consistent through the horizon, irrespective of the pathway that we modelled. A minimum amount of new gas was required in addition to what is currently installed or committed today. And what drives this? If we look at the chart on the top right, we can notice that the average consumption, which is shown in the blue, is relatively consistent through the modelling horizon, but it's really the peak day gas use, which is shown in the gold, increases significantly, and this is primarily to cover the periods of extended renewable droughts. If we just take a quick look at the storage, we can see the storage capacity, that is the megawatts shown in purple on the left chart, remains, again, relatively consistent throughout the horizon. But when we look at the storage capacity range, that is in gigawatt hours, on the bottom right, we see that the range narrows significantly as we approach the end of the horizon, indicating that the optimal gigawatt hours that the model prefers across the whole range of scenarios is relatively narrow. These charts and these results were the results of thousands of discrete simulations that we ran, and as well as the hundreds of thousands of credit hours. And to show how we automated this process, I'll pass over to Kalina, and that's what she'll go through now.
Thanks, Bryce. So Bryce has already mentioned a little bit about how complex and expensive these simulations can be, not only from like a memory use perspective and runtime, but also in how long it takes to set them up. The majority of our models are long-term capacity expansion models, and we're trying to plan the build-out over a 25-year horizon for the national electricity market, so the east coast of Australia. So if we just have a look at what goes into that, you have your typical thermal unit, for example. You're trying to capture over that 25-year horizon certain properties about that unit. How much is it generating? What's its auxiliary use? There's things you want to capture at an annual level, properties that don't change as frequently, for example, fuel costs or build costs or how much capacity is installed. And units will enter and exit, obviously, as they retire, but we have roughly 816 of these units in our simulations. Let's say we're capturing all of those 5 properties so that we can analyze that data over a 25-year horizon, 8,760 hours in a year. So that results in almost 900 million data points. That's just for your generators alone, right? So once you take into account your storages, your lines, you want to capture values of certain constraints, you end up with a lot of data. And there's kind of 2 things you really want to be mindful of here. The first thing is that when you choose to click run on your simulation, you better hope that you've set it up right, because otherwise you're wasting a lot of money and time if you got it wrong. And the second thing is that when you're generating this data and giving it to your analysts, you want to make sure that it's presented in a way that they can easily extract what they need. You don't want them to spend time munging and wrangling data. They should have what they need ready to go. So in order to achieve this, over the last couple of years, we've developed a modeling framework to address these 2 points. On the right here, you can see our tech stack, but I'm just going to go through some of the tools we've built, and you'll see which of those tools they employ as well. So the first thing is on-demand and scalable compute. The main reason this is important to us is because sometimes we will go weeks, potentially even months, without running any simulations. All of a sudden, it's go time, bang, bang, bang. You've got to line up 10 or 20 and get those results back as quickly as possible. So having something like Plexos Cloud, where you have many VMs available of different sizes, is very, very useful. Model versioning and traceability is also important. We have multiple people in the team trying to set up different models with sets of assumptions, and you want to know that if I'm getting the latest version, it is actually the latest version and not 3 iterations ago. And so we've set up source version control to help us manage this. When it comes to developing our demand traces, so those time series data sets, we want to mix and match different components, maybe futures where EV uptake is higher or lower, whatever it might be, and do that in an automated way. And so we've set up what we call a load apportionment tool. It apportions loads, and that's basically a Python application that runs on our servers and lets us do that quickly and efficiently. For our analysts as well, in order to quickly compare relativities between different models and their outputs and have kind of like an easy way to compare that, we've used PowerBI dashboards, which consumes data that is sitting in SQL Server. That's nice and easy to use, and it's also easy for us to share with our stakeholders. When it comes to more kind of specific problems, if we're trying to interrogate hourly data and dispatch dynamics, it might be a very custom or bespoke analysis that we're doing. So in that scenario, we have custom Python scripts and tools that we use to pull out different metrics, specific charts, clustering, lots of that kind of thing. And now finally, tying all this together, a huge component of what we have is a data pipeline that basically takes the simulation results, transforms it, and presents it in a layer that is accessible and readable to the analysts. And so this is our simulation results data pipeline. It uses quite a few things here, as you can see. We're actually in the process of migrating to the cloud right now. So instead of using on-premise infrastructure, we will be using Azure and Snowflake, and I'll talk about that in a second. But I just want to emphasize that you can have all of these tools, but tools take time to build, and they take time to maintain. So you want to make sure that they are actually serving a purpose and that you've developed standard processes and ways of working that make the most of it. You want the tools to work for you, not the other way around. So just to quickly go through our current data pipeline and the migration process. So at a high level, what we have is our simulation results sitting in Plexos Cloud in the external environment. We have a Python application, a custom one, that runs in an Azure container app. And what it does, it picks up those files as they are and dumps them in our blob storage. Then we have an ingest pipeline, which is orchestrated by Snowflake tasks. And what it does is it picks up those files, mainly parquet, and puts them into Snowflake, which is a data warehouse. If you're not familiar with Snowflake, think like database on steroids, basically. And what it's actually doing is basically just picking it up and putting it into data tables that you can query like you would with SQL. We then have a transform pipeline that basically picks up that data in the raw queryable layer and moves it over into our curated layer, which is where you have your business logic. You've set things up so your analysts can easily analyze your results, and it's nice and accessible for them. And they will, connect to that through PowerBI, through their bespoke Python tools and charts, and that's our infrastructure at a high level. And the reason we have begun this migration process is because we were finding that it was taking a long time to load our data in to our on-premise SQL server. We were literally running out of storage, like the physical racks can't just put in anymore at that point. And it was taking a long time to query and get the insights we need, especially like that high resolution hourly data. So for us, moving to something that can scale, for example, you can really crank the warehouse when you need to interrogate more detailed data, and then use smaller warehouses when you don't need it. It's very useful for us. We focused a lot, I guess, on what comes out of our simulations, but the next step for us is to try and improve the way we set them up and try and automate some of the processes around our models. So if we think about how we currently run things in Plexos, you have your Plexos database that exists as an XML file, and we have our traces, like your time series data sets, which essentially sit in your CSV files. Your analyst will go and build that model in Plexos desktop. That file will then get uploaded along with those traces to Plexos Cloud when they want to run a simulation. And they have to manually trigger that in Plexos desktop. And then once it's all uploaded, because both of those things need to get sent to the cloud, they then need to go to Plexos Cloud and manually hit run so that that simulation is now triggered. So we've thought about, what if we approach this from a different perspective? With this Plexos database, what if we break it up into two components? We have what we call a shell, which is essentially like your network representation, what generators you have in it, what storage is, what lines, the topology, essentially, of your network. And then you can have separately your Plexos object properties, which is the actual information pertaining to those units. So fuel costs, build cost, entrance and exit dates. And so your analyst can still use Plexos desktop for setting up that model, because it's user-friendly and that's really what it's made for. And then they can use Excel to essentially edit and update those object properties based on different scenarios. And we will have a tool, currently proof of concept, but going quite well, that will essentially take these two components and use the Plexos Python SDK. And what it basically does is it takes the shell and then inserts those object properties and creates like a complete Plexos database. At the same time, once it's run that build process, because you're just executing it with like a command, it can do some verification as well. Like, hey, you missed some units, or some of your fuel costs are, not as expected. And after that, it can automatically queue your simulation and send it to Plexos Cloud. Another huge advantage of this is that those traces, which we have quite a lot of depending on scenarios we're running, at the moment sit on our hard drives, and it's getting very full. And so we can use Plexos Data Hub, which essentially lets us store all our traces in there. And then when we're actually running the simulation, all you're doing is referencing the location and data hub. So those traces aren't even like going through your network, you're not even touching them. It's automatically getting loaded into those Plexos Cloud VMs when the simulation starts to run. So this is what we're currently working on. Hopefully, we will potentially be able to talk to you about this maybe next year and see how it went. But yeah, that's kind of what we're working on at the moment. So that brings us to the end of our presentation. Are there any questions?
Yeah, thank you. It's Brian from Transgrid. So it's great to see that you use GitHub for version control. Do you have any measures in place within Powerlink to ensure data security?
Sorry, what was the
data security with GitHub for version control?
For data security?
Yeah, yes, true.
Yeah, so I guess you don't kind of store your data in GitHub. So we store at the moment like our Plexos files. Essentially, data security is managed through your, I guess, IT infrastructure, in that our team has specific project in Azure DevOps, and that is only accessible to people in our team. So all of that, I guess the models and all of that source code has to be explicitly granted access when someone needs access. So only within our team can we actually access that, and that's the way that's managed. But does that answer your question? Or?
Yeah, but when you use GitHub for version control, you probably will upload some codes into the cloud.
Into the cloud,
GitHub.
yes, yeah.
So how do you ensure the security of that data?
Oh, sure. So, I mean, that's your IT infrastructure. So you have role-based access control. You have network perimeters. You can't access it unless you're on the VPN. So you've got firewalls. You have layers and layers and layers of security. I know that, I guess, cloud, there's a big kind of fear around the fact that your data is sitting on someone else's servers, but many providers now have the option to either keep it purely in Australia, but further you can actually have your own like private cloud that essentially they deploy and is completely cut off from their own network. So for some industries like defense, you actually have options as well to deploy those kind of systems.
Thank you.
No worries.
Superb. Was there any more questions for Bryce and Kalina?
Hi, thanks for the presentation. I have an ask regarding the layer approach for the long-term planning. From the linear approximation to the realistic dispatch, is that a sequential problem that you solve one by one, layer one by one, or do you do an iterative process?
Yeah, good question. So the realistic dispatch, which is effectively... I'll just jump back to that slide and take a while. The realistic dispatch effectively is the last step of the process. Sorry, a lot of animations.
My bad.
Here we go. Okay. So the realistic dispatch effectively is the last step of the process, which takes into account all of the learnings that you've done prior to that. So I would say the realistic dispatch would be the final step. And when we speak about that, it's effectively about getting the final set of results across the full modeling horizon. So we run out to 2050 at an hourly resolution through Plexos. So you can imagine that's quite computationally intensive, and that's why we need to use the cloud for that. But to your question, do we go back in the other steps? We definitely do, yes. So sometimes we'll reach a point where, for example, we start to overlay the deliverability constraints, and then we realized there may have been something that we missed in the linear sensitivity analysis. So we look to explore the whole range of modeling options with the best knowledge we have at the time. But obviously, as you start to approach the problem, you learn new things. So there may be instances where, yes, we do have to go back. Or, for example, under this step, if we pass this on to our system planning team and they say, look, the build out that the modeling is indicating with this level of deliverability constraint is overly constraining certain parts of the network, that's when they might give us a constraint. So we have to go back perhaps a step or two to the linear and say, well, what would the least cost transmission build out be under this step, given the understanding of these new deliverability constraints? So it's not a full linear process, but the idea is that, as you learn more across each step, you hopefully go back less. But I think under any modeling, when you're trying to understand the landscape and you're looking out in such a horizon, naturally you learn things as you go along the way. So it does necessitate going back at some point. And I think it depends on, what you learn.
Hi, do you mind going to the results slide where you show the build-outs? You need to go through more animations. Thank you. The storage you have indicated there, it seems to be on all the time points you have 8 to 23-hour storage durations. I'm curious to know why you didn't model anything under 8, given that...
Yeah, really good question. We did. But given the model values megawatt hours over megawatts, we found the model as part of a least cost system solution didn't value those shorter duration storages purely because on a $1 per kilowatt hour basis, the 8-hour storages were the cheapest.
Okay, thanks for that. And the 23-hour, is that a pumped hydro or is that like a long duration?
It was a long duration storage. So we did model some long duration storage options like pumped hydros, but effectively we grouped them into what we considered those longer duration bucket. But we found the model only built 8-hour batteries.
Okay, yeah. Because the really long ones like the 23-hour, there'll be technological, dependencies on that, like unknowns, as well as the fact that, as well as the cost forecast. So that is an interesting one. But no, thanks for answering that question.
Yeah, there was a fixed large storage object, which we did force into the model based on some policies at the time. The formatting didn't quite fit there, but effectively that's that big jump that you see.
So when the model says or finds that 8 hours is the optimal solution, did you actually force the model to say, well, but what we are seeing getting billed is 4 to 6 hours, so what happens then? So ran a few sensitivities?
We did run a number of sensitivities on shorter duration storages, and we also did run sensitivities as well on behind the meter batteries. But I guess what we found in our modeling, when you're looking at a whole system least cost, without a portfolio view, the model again just values what is cheapest on a $1 per kilowatt hour basis. So we were looking at this from a whole of system. I think if you were looking at this from a more, smaller portfolio, there would be greater trade-offs. But that's not something that we considered in this form of modeling.